Hello, chemistry students. Today we're going to talk about gas laws. And the first thing we're going to talk about is kinetic molecular theory of gases. Kinetic molecular theory is based on the idea that particles are in constant motion, which means they are constantly moving. Kinetic energy is the same thing as movement. The first postulate, or first theory, is that gases consist of molecules whose separation is much larger than the size of the molecules themselves. So most of the volume of a gas is empty space. So if we take this example over here, we have a gas molecule right here, and the space between it and another gas molecule is much, much bigger than the size of the gas molecule itself. The second postulate is that particles in a gas constantly move in straight line paths and in random directions. So they don't twirl around in a circle like this. They are very random in their motion, and they constantly move in a straight line until they hit something, and then they move in a straight line in a different direction. Third postulate: particles in a gas collide frequently with the sides of a container and less frequently with each other. A gas molecule will more than likely hit this side of a container before it will hit another gas molecule. And the collisions are elastic, which means that energy is only transferred. It is neither lost nor gained. So if a gas molecule hits another gas molecule, it will transfer some of its energy to the other gas molecule. So the other gas molecule will start moving faster, or it will start moving slower if it gains some energy from the other gas molecule. But what will not happen is when the gas molecule hits the side of a container, it will not go slower or faster than before it hit it. So the gas molecule will have the same speed after it hit the side of the container than it did before. The fourth postulate is that gas particles do not attract or repel one another. So this gas molecule right here is not attracted or repelled by any other gas molecule in this container, and that's because they're not close to each other. Fifth and last postulate is the amount of kinetic energy in the gas is directly related to the temperature of the gas. So as kinetic energy increases, the temperature increases. As kinetic energy decreases, the temperature decreases. As the movement of the gas particles increase, the kinetic energy increases, and therefore the temperature will increase. All gases at the same temperature have the same amount of kinetic energy. So the things you need to remember: these postulates describe an ideal gas. Real gases, or gases in the environment that we see, act like ideal gases at normal temperatures and pressures. But once the temperature of a gas starts to get very, very low or very, very high pressure, the behavior is not like an ideal gas, and they behave very differently. So at low temperatures and high pressures, gases are not ideal. So let's talk about low temperatures. Cold gases, or low temperature gases, they move slower because, remember, temperature is directly related to the kinetic energy of a gas. So the kinetic energy, if it has a low temperature, it will have low kinetic energy, which means it will be moving slowly. And when they move slow, the gas particles start to attract one another. And when they begin to attract one another, they have less space between them, which violates the postulates of an ideal gas. So they start to not behave like an ideal gas. So we have over here in this picture, and if you notice, once it becomes a higher pressure, the gas molecules are closer together. If they begin to get closer together, they start to attract, just like in low temperature. Definitions: gases. It's a phase of matter with no definite shape or volume. Kinetic energy, like I said before, is the energy of motion. If it's moving, it has kinetic energy. Pressure, the force exerted by a gas per unit area on a surface. Partial pressure, we're going to talk about this more later on in a different video. It is the pressure of one gas in a mixture of gases. So if we have a container of oxygen and hydrogen and we want to know the partial pressure of just the hydrogen, we can find that. Temperature must always be in Kelvin. It is directly related to the amount of kinetic energy of a substance, or how much it's moving. An STP is standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. Okay, our gases can be described by 4 variables. First variable is pressure. We denote that by the letter P. And the units for pressure are atmospheres, which is denoted by ATM, kilopascals, which is kPa, and millimeters of mercury, which is mmHg. Those are the symbols for pressure. The second variable is volume. We denote that variable by the capital letter V. The units for volume are liters, milliliters, cubic centimeters, and you need to remember that 1 cubic centimeter is equal to 1 milliliter. And by the way, cubic centimeters is most often used now in a medical situation like doctors or hospitals or veterinarians. You may hear them say, well, just give them 10 cc's of this fluid or this medicine. cc stands for cubic centimeter, so 10 cc's is the same thing as 10 milliliters. Third variable is temperature, denotes by the capital letter T, and we always put temperature in Kelvin. You've heard of Celsius and Fahrenheit. If you are given those temperatures, you must convert them to Kelvin first because our ideal gas laws are always in Kelvin. Our fourth variable is the amount of something, and we've already talked about this before. The amount is the variable N, and the units are moles. So if you see the variable N, it will be talking about the moles of that gas. Conversions. Temperature, it must be in Kelvin units for any calculation in this unit. And you have to remember that Kelvin is the same thing as Celsius plus 273. On your star chart, you will see that 0 degrees C is equal to 273, but you need to know how to convert. So an example, a gas is at 15 degrees C, and we need to convert it to Kelvin. So Kelvin will equal 15 plus 273. So that is 288 Kelvin. Okay? Temperature is 288 Kelvin. Next example, a gas is at a negative 150 C. So our Kelvin temperature would be negative 150 plus 273, which is equal to 123 Kelvin. It doesn't matter what units pressure is in and what unit volume is in, as long as you use the same unit within a single calculation. Now, 1 atmosphere is equal to 760 millimeters of mercury, which is also equal to 101.3 kilopascals. That also is on your star reference sheet. I do not expect you to remember it or memorize it. Okay, so an example, a gas is at 432 millimeters of mercury, and we have some other words in here, and then later on it'll say its new pressure is 4 atmospheres. So if you notice, we know this is a pressure because it's in millimeters of mercury, and the units for pressure is millimeters of mercury or atmospheres or kilopascals. So it doesn't matter if we use millimeters of mercury in this problem or atmospheres, but they have to be the same. So we will have to convert. So let's convert 432 millimeters of mercury to atmospheres. And you're going to use your dimensional analysis this way because we're so used to doing it, okay? So millimeters of mercury goes on bottom because whatever is in the top left goes on the bottom right. All right, we want to convert to atmospheres, so I'm going to put ATMs up at the top, atmospheres. Now I need to fill in these numbers, and I need to look up here, 1 atmosphere, so I'm going to put a 1 up here, is equal to 760 millimeters of mercury. So I'll put 760 right here. The answer is 0.568 atmospheres. So instead of 432 millimeters of mercury, we're going to use 0.568 atmospheres. Okay, our next example, a gas at 432 millimeters of mercury, its new pressure is 265 kilopascals. Well, let's go ahead and I'm just going to choose one. Let's choose kilopascals that we're going to convert to millimeters of mercury. So 265 kilopascals, and we're going to convert that to millimeters of mercury. Now remember, it doesn't matter which one, just as long as both of them are the same. Kilopascals, whatever units we have up here, we're going to put down here. And we want to convert to millimeters of mercury, so I'm going to put that up here. That's an HG for mercury. And we look up here on our conversion, and we have 760 millimeters of mercury, so I'm going to put that number right here, is equal to 101.3 kilopascals. And that answer is 1,990 millimeters of mercury, because my kilopascals go away. So now this, instead of using 265 kilopascals, I'm going to use 1,990 millimeters of mercury, because 990 millimeters of mercury is the same thing as 265 kilopascals, and I need both of my pressures in the same units.